This lesson's about power and efficiency. You'll be able to define those terms and solve problems using power and efficiency. So first, let's think about raising an elevator. If you were in an elevator down here and you were being raised up through a height to get to another floor, then the work that would need to be done is the change in energy, the change in gravitational potential energy, which is equal to mg delta h. That's the amount of work that would need to be done on the elevator to raise it this height. Notice, however, that there's no indication of time here. So the amount of work or the change in energy is the same if this happens really quickly or if this happens very, very slowly. And clearly that's going to make a difference to our experience riding in the elevator. So we need another way of thinking and talking about that, and that way is power. Power is the rate at which work is done, or alternatively, the rate at which energy is transformed or transferred. The average power over a time interval is equal to the work done in that time interval divided by the elapsed time, or equivalently, because work is transfer of energy, the change in energy divided by the change in time. And we've got joules in the numerator here and seconds in the denominator, so the unit of power is joules per second, which is given the special name of a watt. Let's look at an example. We're asked to find the power needed to raise a 1,000 kilogram elevator up 15 meters in 8 seconds. So the power is going to be equal to the change in energy divided by the elapsed time. Here, the change in energy, if we assume that this is moving with constant velocity, is only going to be the change in gravitational potential energy, mg delta h, divided by the time. If we plug in our numbers, that's 1,000 kilograms multiplied by 9.81 meters per second squared, multiplied by 15 meters of vertical displacement over 8 seconds. And if we put that into our calculator, we get something close to 18,394 watts, rounding a bit, and rounding more. Let's imagine there was a decimal there, so this is to two significant figures. We could call that 18 kilowatts. Okay, so there's an example of finding power. Also notice that the average power formula that we've given includes work, and we've defined work earlier as the product of the displacement times the component of the force that's parallel to that displacement. And if we take this part separately as displacement divided by time is our formula for average velocity. So the formula here simplifies to the parallel force multiplied by the velocity. This is now another way of calculating average power. Multiply the parallel force by the velocity. Here's an example. A jet engine develops a forward force of 320,000 newtons. What's its power output when flying at 250 meters per second? This is really just a plug and play type problem with our new formula. The average power is equal to the component of the force that's parallel multiplied by the velocity. And in this case, the component of the force that's parallel is the whole force, so 320,000 newtons multiplied by 250 meters per second, and we just plug that into our calculator, and we get 8 times 10 to the 7 watts, or 80 megawatts. Okay, so there's an example using this different version of the power formula. Now let's talk about efficiency. Efficiency is defined as the useful work you get out divided by the total energy you have to put in to get that useful work out. Or equivalently, because you could divide both the numerator and the denominator here by the same time interval, because they're happening over the same time interval, that would get you from work or energy to power, because power is the time rate of change of energy. So equivalently, efficiency is the useful power out divided by the total power in. Let's look at an example. In the first part of this example, we're just asked to find power output, not efficiency. We've got a 70 kilogram student who runs upstairs covering a vertical distance of 4.5 meters and doing that in 4 seconds. First, we're asked to find their power output. So their average power is going to be the change in energy divided by the change in time. And this is just another bit of practice at what we saw already, because if they run at constant velocity, their change in energy is just their change in gravitational potential energy. So similar to before, we multiply their mass by the acceleration due to gravity, multiplied by the change in vertical distance, or the vertical displacement rather, and we divide that by the time. Now, I'm just going to mention that when we do this, the first step of our calculation gives us a numerator of 3090.15 joules. We're going to need that in a bit, so I'm going to just put that there. We divide that by 4 seconds, and we get approximately 772.5 watts. And if I imagine that there was a decimal there so that this is two significant figures, then I'd get 770 watts. So that's the answer to the first part of the question, just more practice on power. But the second part brings in efficiency, and it says if 20% of the student's consumed food energy goes to raising him up the steps, how much energy from food did he need to take in to do this? In other words, the efficiency is 0.2. That's what that is telling us. So if we go back to the energy, careful, it's giving us energy information, not power information. So we have to go back to the energy that we had above, which was 3090.15 joules. And that's divided by the total energy consumed, which is what we're looking for. We know that's equal to 0.2. Rearranging then, the total energy is equal to 3090.15 divided by 0.2, and that's approximately equal to 15,451 joules, or to two significant figures again, about 15 kilojoules. By the way, in terms of food energy units that you might be more familiar with, that's about 4 kilocalories, or the 4 capital C calories that you see on the side of food products. Okay, so there is an introduction to power and efficiency.